strong, but with a noticeable scatter. So we know that dust is affecting the Lyman-alpha transfer, but at fixed dust content, there's still, or fixed reddening, basically, there's still quite some scatter, right? And how much Lyman-alpha actually escapes. Right? And I think the nicest illustration of the scatter that we have in the Lyman-alpha escape fraction is illustrated with this galaxy that we've heard about before quite a few times, 1 Zwicky 18, right? It's a nearby galaxy, very metal poor, very little dust, very little reddening. So according to this previous plot, it should have a very high escape fraction of Lyman-alpha, right? So it should be the ideal Lyman-alpha emitter. So then if you take the spectrum of it, it actually looks like this, right? So it's the perfect anti-Lyman-alpha emitter, basically. So in many ways, this is very disappointing, right? Because this galaxy you would naively have expected this to be sort of the best candidate. It would be like a high redshift galaxy, or like a very high redshift galaxy, possibly even like a POP3 galaxy. That surely would have had a lot of Lyman-alpha photons coming out, but no. Now, fortunately, so tomorrow Matthew will actually show surprising evidence that this galaxy has POP3 stars in it, right, Matthew? That's too bad then. In any case, okay. However, this is not the whole story. We have other nearby galaxies that are considerably more metal-rich and that have Lyman-alpha emission, right? And one thing that distinguishes these galaxies from I won't look to the back of the room anymore. One thing that distinguishes these galaxies from 1 Zwicky 18 is that we can see that there's evidence for outflows, right? And as I mentioned, in several ways. So these galaxies show blue-shifted absorption lines in some of the low ionization metal species, right? So we're looking at the galaxy, we see the absorption, which is blue-shifted, and that means that there is enriched material coming at us, right? So it's being blown away from the galaxy. So there's material, low ionization, in low ionization states, so with temperatures where hydrogen can be neutral, that is outflowing, right? And what you can see in this particular spectrum, which has been truncated, is that the Lyman-alpha is actually redshifted with respect to systemic velocity, right? And as I was mentioning this morning, is that's a telltale characteristic of Lyman-alpha scattering through an expanding medium, right? So this plot actually shows us that the Lyman-alpha is actually interacting with this outflowing gas, and as a result, it's getting redshifted, right? And you also see in addition to the redshifted Lyman-alpha emission, we also see the center of the Lyman-alpha absorption that we see with these nice broad damping wings is again blue shifted with respect to the systemic velocity, right? So evidence for outflowing neutral hydrogen gas and evidence that the Lyman-alpha is interacting with this gas and being redshifted as a result. So these are some of the examples of these redshifted low ionization metal transitions. I don't actually know what these are, but in any case, this would be the systemic velocity, and you can see that these lines are redshifted. Right? So Matthew will explain which lines these are. In any case, so we have so this is almost consistently this picture. Right? This picture is very consistent, right? The nearby galaxies that have Lyman-alpha emission, we see the redshifted Lyman-alpha emission lines and the sort of blue-shifted absorption troughs, right? And the same in these other metallic lines. So just this very clear evidence that the outflows are promoting the escape of Lyman-alpha, because the galaxies that do not exhibit Lyman-alpha in emission consistently do not have this kind of nice outflow signature. And this was very nice in this paper from 1998 by Daniel Kuhnt, and also Heikki Matek has also done some very nice work on this, not mentioned here. So this strongly suggests that interstellar gas flows are we've already heard that as well, but that it's both the distribution of neutral gas, but the kinematics actually has a very important role in letting Lyman-alpha photons escape. And the picture here is that what I was discussing this morning is that you have Lyman-alpha photons are scattering, and they're diffusing in both real and frequency space, right? And as they are diffusing in frequency space, they had a much easier time escaping, right? Because they sort of ended up further away from line center, where the absorption cross-section is much reduced. Now, if you have gas kinematics, if the gas is moving, then you actually have a shortcut of, you provide a shortcut with which you can get Lyman alpha photons away from line resonance. Right? So you don't have to wait for the, say, 1/1,000,000th scattering event, which bounces a photon far enough into the wing, which allows it to escape. You actually have the gas that is moving, that is doing it almost for free. Right? So, even though dust clearly plays an important role, we see it's anti-correlated with Lyman alpha. We see it's correlated with Lyman alpha escape. So the more dust, the less Lyman alpha escape. But there is a big scatter in this relation, right? And this scatter is very likely related to the gas kinematics. Right? And we see this at basically all redshifts, right? So this was recent work by, let's see where you are. I cannot. He's not here. Oh, you are, sorry, okay. So what is nice about this is that you have joint H-alpha and Lyman alpha observations. And the H-alpha is a non-resonant line, right? So H-alpha is not scattering. And we know that H-alpha is produced in recombination cascades, like the Lyman alpha. So we think that the H-alpha gives us, basically an indication of what the Lyman alpha line should look like if it were not scattering, right? So it really allows us to distinguish, or it allows us to identify very clearly what the impact of scattering is, right? And you have. So what you see is that Lyman alpha is again redshifted compared to H-alpha, right? Often. Again, a very clear signature of Lyman alpha photons interacting with outflowing gas. Right, and this panel here actually shows you just a sample of Lyman alpha selected galaxies and continuum selected galaxies, and what the typical velocity offset is of the Lyman alpha line. Right, and the typical velocity offset is of order of a few hundred kilometers per second for Lyman alpha selected galaxies, and for continuum selected galaxies it's a bit larger. I will not going into this much in this talk. But the main point is that most of these lines are actually redshifted, right? All of them. This is 0. Almost all of them are redshifted. So, we have this schematic picture in which Lyman alpha escape is very much aided by the presence of outflows, right? And this is I think, famous cartoon that has been shown by Max Bettini for many years, right? So the picture is you have these young hot stars that are ionizing the environment here. Recombinations power Lyman alpha radiation, and then basically the Lyman alpha scatters through this outflowing gas, and as a result obtains a redshift, right? And what you often hear is that, if you have an observer sitting here, the absorption takes on the front, so you have blue shifted absorption, as I was explaining earlier. The Lyman alpha scatters on the far side of the outflow. When it does that, it gets a redshift and it can escape, right? In a way, it's a bit different than the scenario that I was describing this morning, but in the scenario I was describing this morning, you had an outflow that was basically everywhere, right? There was outflowing gas everywhere. So the outflows in general redshift the Lyman alpha line, right? And the backscattering is just a special case of that. Right, so I mentioned this, and this is again a plot showing the mean velocity offset of interstellar low-ionization metal absorption lines, right? And they're all blue shifted, with an average blue shift of about 160 kilometers. So this is from a sample of about 90 Lyman break galaxies by Steidel et al. Right? And again, the Lyman alpha and these same galaxies, the Lyman alpha emission that we see in these galaxies, not all of them have Lyman alpha emission, is again typically redshifted. So I'm just cannot say enough that why these outflows are so important. Now what I'm going to show you here is a movie. It's a simulation. It's a very small scale simulation. It's a grid-based simulation in which it's about 100 parsecs across, or a few hundred parsecs across. The resolution is 1 parsec. And what people have done is you have a multi-phase interstellar medium, and you set off supernovae explosions inside this ISM. And the main purpose of this movie is to demonstrate that once you set off supernovae explosions in a multi-phase medium, you actually it becomes quite messy, right? Like the kinematics of what you see, this yellowish stuff that is coming out, is the modeled H-alpha emitting gas. So this is like the cold gas that should also be scattering the Lyman-alpha radiation. Right, so this is what this movie is showing is that this is actually remarkably complex. So what happens here is that you have a multi-phase medium. The supernovae explosions sort of create this overpressurized bubble which start expanding, start pushing out dense gas that already exists in the ISM, and that sort of gets stretched out in these radial directions. And that's actually what is shown here. Now I'm also showing this other plot from Fujita et al., which I think illustrate nicely why this is such a complex problem. Right? So we know that the kinematics of neutral hydrogen gas and also the distribution of neutral hydrogen gas is what is very strongly affecting Lyman-alpha radiative transfer. Right? So what I'm showing here is just from a very similar situation such as this one. It's a different one. But what these authors were plotting is the outflow velocity of their cold neutral gas clouds. So each point is an individual cloud in these simulations. And the H column density of these clouds, right? If they're very dense, so I think most of them are actually neutral. Right, so this quantity here is the column density. It's one of the most important, it sets the optical depth to Lyman-alpha scattering. Right? The velocity is the outflow velocity of the wind. So that again also plays a key role in the Lyman-alpha transfer process. And the point here, this is a parsec resolution, right? So this is very high resolution, but this is 1.1 parsec resolution. Same simulation, right? So both quantities that are regulating Lyman-alpha escape are actually affected a lot, right? And then when you go to this resolution, you start worrying about the effects with molecular clouds, magnetic fields, etc. Right? And the main point of this is not to scare you, but it's actually to just, I think, just to illustrate why first principle modeling of this process is still very difficult. Right? And I think we're moving closer and closer as a community, but it is very difficult. So that's why this sort of sets me up for the, all right, so actually what I like about this is this simulation actually looks very nicely like M82. Right? So this is actually H-alpha emitting gas here, I think, this reddish stuff. It looks nicely the same. The scale is a bit different, this is smaller, but just to illustrate that this complex, messy, multi-phase outflowing stuff happens in nature, right? We see it in nature. This is not like all made up. So that's why, because of the complication of modeling this from the bottom up, the common approach is to go top down, right? So you sort of say like, okay, at least that's my interpretation of it. This process is so complicated, we're going to represent this whole process with a sort of subgrid representation of what is happening on these small scales, right? And then later, we can wonder like what this actually really means, right? So I think this is a very valid approach. So the shell model consists of a central Lyman-alpha source. It's actually usually a point source, but this is just a big point. Right? So the Lyman-alpha source is sitting here. It's surrounded by a geometrically thin shell. So the thickness of the shell is usually 10% of the radius, but in practice that doesn't really matter, like how thick it really is. The shell is characterized by column density, a dust optical depth through the shell, an outflow velocity, and there's a turbulent broadening parameter, which is basically a simplified representation of turbulent motions inside the shell. Right? Now, in most cases, B is much smaller than V, so it is said that the shell is actually kinematically cold. Right? So these are 4 parameters, and then you have 2 additional parameters that you need to fully describe your Lyman-alpha emitting source. Right? You have your equivalent width of the line, which is sort of the strength of the line compared to the continuum, right? And the full width half max of the line. Right, and so An was one of the first to really show, or was the first to really show that this model really can be used to nicely reproduce some of the observed line profiles that we see. Right, so I'm going to show some stuff that we've been working on as well. I'm just going to do some advertisement. You can actually do shell models yourself online if you want. So this is just a particular parameter combination of shells: tau dust, the intrinsic line width, intrinsic equivalent width, hydrogen column density, velocity, temperature. Temperature you should think of as this B parameter that I showed. And just to show if you go online to this website, bit Lyman-alpha, right? I'm not sure if it's actually still online, I think so. You can, for example, shift these buttons around and see the effect on the resulting spectrum. Right? So this is a static shell. The line is initially quite broad. It is Gaussian. Sigma is 300 kilometers per second, so the delta V is here. Right? And as you increase the column density, you start to see this double-peaked profile emerging, right? That we discussed earlier. You get a bit of broadening. You remove photons from line center, you get broadening. Now let's pick a column density of 10 to the 20 and increase the outflow velocity of the shell. Right? So you can do that as well. Right? And you can, as you increase the outflow velocity, you slowly start decreasing the blue bump, and you increase the red bump. Right? You also see you shift and broaden it a little bit. Right? There it goes. Look at the blue bump actually isn't, well, it goes away, but quite slowly. Right? Now these models are based on the grid, I think, of 10,000 models that sort of span this particular parameter space. You can post-process the other parameters. And so then you have, in principle, a tremendously large grid, right? So you can quite efficiently fit these line profiles and see what the constraints are on individual line profiles. So this is an example of a green P galaxy, just illustrating again how well this shell model can work. Right? With an outflow velocity here, for example, of 100 kilometers per second, column density of 10 to the 19. Right? It works for a redshift 5.4. This is not a P, this is a monster. I mean, in all I think, meanings of the word. This is a superluminous Lyman-alpha emitting galaxy. This is a paper that is in prep by Ian McGreer. Right? And this is CR7 that we looked at recently. And I think this is a very interesting source for many reasons. I will not talk about it much. The main thing here is that CR7 has shell model parameters that are very similar to what we see in the green Ps. Right? So I think that, to me, that already illustrates the utility of the shell models. Right? It provides you with a quantitative way of describing a Lyman-alpha line profile like this. So in this case, you can say that CR7, a Lyman-alpha emitter at redshift 6.6, which has been speculated to be associated with both POP3 stars and direct collapsed black holes. The scattering medium the medium that is scattering the Lyman-alpha photon seems very similar to what is present in green P galaxies, right? So that's, I think, is telling us something, but yeah, we're going to see, we're going to work some more on this in the future. Okay, so one thing that we're working on now is trying to understand why this works so well, right? So one thing that we're doing now is not fitting shells to data, we're fitting shells to other models, right? And here's an example of a fit of a shell model to a clumpy outflow model, for example. So this is a multi-phased model that I was discussing earlier as in the spirit of Neufeld. Right? You give it an outflow velocity, you put a Lyman-alpha source in it, you compute the emerging spectrum, you fit a shell to it, and then compare the properties that were actually associated with the clumpy outflow model and compare it to the shell. And in this case, it actually works quite okay, right? The column density in the let's see. I'm actually confused. I forgot which one is which. Oh no, this is the shell. So for a column density of 10 to the 20 in the shell, the actual column density through the clumps was 4 by 10 to the 19. Right? So that's actually pretty close. Outflow velocity is different by a factor of 2.5. The sigma is tremendously different, right? And that's actually interesting because, so here, for example, the shell models prefer a sigma of 300 kilometers per second, while the clumpy outflow models, 50 was enough. Right? I think this is quite interesting because there are some galaxies which can only be fit with unusually strong, unusually large intrinsic line profiles, right? Which is actually puzzling on many levels, but I will not talk about this today. But just to show you that there is some, that this is also something that we are working on, and I think others are doing this as well. And I think this is a very important question, right? What these shell model parameters actually mean, because for one reason, if we want to actually infer something about the medium, the scattering medium of Lyman-alpha emitting galaxies, then I think it's important that we understand what these parameters actually mean, right? And right. So this is all describing interstellar radiative transfer, and we know that it doesn't really stop once Lyman-alpha photons escape from the dusty ISM. It doesn't stop there, it's just the beginning. Right? And because it's just the beginning, it's really important to understand interstellar radiative transfer because it sort of provides us with the initial conditions for subsequent radiative transfer. Right? And this is one, well, for this reason, this is one of the reasons, but this is one of the reasons why MUSE is so great, right? So this is a data from this recent MUSE paper. And what is shown here is, I think, the UV continuum, right? And the Lyman-alpha is much more extended. Now this is the UV continuum, right? Someone knows this? Yeah. Okay. Oh, so the red is HST UV continuum. Wow, okay. Cool. So Lyman-alpha is much more extended than the UV continuum. And, this is actually, I'm not sure if I said this, but I've definitely said it over lunch at some point, and over coffee at some other point, that what is remarkable about the situation that we're in now is that Lyman-alpha seems to be popping up everywhere, right? Like you look deep enough with MUSE and there's Lyman-alpha just extending out to very low surface brightnesses, but very far. And that's quite different than when Matthew was talking about the early days of Lyman-alpha, and Lyman-alpha was nowhere to be found, right? Now it seems complete opposite. It's everywhere, and there's more of it than we thought, right? So I think it's very cool, actually. The thing is that we actually don't know at all what these things actually, well, we don't really understand. Let me be a bit more, give ourselves a bit more credit, but we don't really understand what these halos actually are, right? Some people have argued that these are satellite galaxies or cooling or a combination thereof. Masami mentioned this already. So we posted a paper actually last night with Luis that's arguing that there can be a significant contribution from fluorescence. Right? And in earlier years it has been argued that we should see spatially extended Lyman-alpha emission from around star-forming galaxies because we expect photons to scatter in neutral gas that exists around these galaxies. Right, so there's several explanations at this moment. But what is interesting about this is that each of these processes, satellite galaxies, cooling, scattering models, etc., they give you, in terms of like, they will likely give you very different spectral signatures. Right? If you have cooling, for example, cooling radiation is associated with inflowing gas. So as I was talking about this morning, there you would expect a more blue-shifted component on average. Right? I mean, this is all to first order. But there should be differences in terms of the spectra for all these different processes. Right, so I think this is exciting. At the same time, as I'll talk about tomorrow, scattering, for example, uniquely should give you different polarization properties than in situ production of Lyman-alpha. Right, and polarization measurements have already been made, and polarization has been detected for some sources, not for others. But there are ways to distinguish these mechanisms. Right? Right. So one thing we do know from the Lars sample is that there is scattering beyond at larger radii, from larger distances from galaxies or whatever you want to call it, like from the stars, right? So this is one of the Lars galaxies, Lars 1, and the Lyman-alpha is much more extended in the UV continuum and the H-alpha, right? So there is scattering further from the galaxy. That's definitely going on at low redshift, and we expect it may at least play a role at higher redshift as well. Oh, right. That was my own wake-up call. I just I'm not going to invite a question this time. So I think the scattering. Oh, now I'm not going back because then it happens again. But I would love it so much, actually. But okay, I'll do it anyway. So scattering on these, I guess the scattering relatively close by to the galaxy, if it's scattering, gives rise, or in this case it's definitely scattering, gives rise to Lyman-alpha emission that we can detect. Right? So modeling this is going to be, it's interesting, and you really need to do the full radiative transfer to actually model this and understand this, right? Okay, there we go. If we go to larger scales, to intergalactic radiative transfer, things simplify. Right? And typically we have defined intergalactic radiative transfer as happening beyond the virial radius, or slightly further away, 1.5 virial radius. I think 2 virial radius has been used. Christoph, what do you use? You use 2 or? Sorry? I just don't use it. You don't use it? Oh, good for you. Right. So the main reason to make this distinction is that when Lyman-alpha photons scatter beyond this distance from the galaxy, it typically is scattered at surface brightness levels that are so low that it doesn't really matter for observations. We will not be able to observe it anyway. So you might as well just pretend that these photons were destroyed. Right? So this really simplifies the radiative transfer. We don't have to take into account of scattering. All we can do is say, okay, if I want to predict my model luminosity in Lyman-alpha at some frequency nu, I take the intrinsic luminosity or whatever comes out of the galaxy or out of the CGM or ISM, and I just multiply it by the transmission of the IGM at this particular frequency. And this method is sometimes referred to as the e to the minus tau method, right? And it actually, for modeling intergalactic radiative transfer, modeling reionization, etc., it works just fine. You know, like I think it's, yeah. So what does it look like? So if you talk about intergalactic radiative transfer, you can basically say it's very equivalent to intergalactic opacity, right? And X has been talking a lot about this already, so I don't have to say much about this. Except that from the Lyman-alpha force, we know that the IGM basically has non-zero opacity for photons that are emitted on the blue side of the Lyman-alpha resonance, right? So if you're a higher energy photon, you will redshift into line resonance due to the Hubble expansion, and at this moment, once you reach the resonance, there's a finite probability that you get scattered out of the line of sight, and you're basically lost, right? So this flux is lost, right? And the simplest way to illustrate this is 100% transmission on the red side, sharp transition on the blue side at a fixed value, right? And in reality, of course, from X's lectures, we know that the actual opacity is fluctuating like crazy around this mean value. So what has been done, what is often done, is that people say they correct for the IGM opacity by suppressing any radiation that comes out on the blue side of the line by some constant factor e to the minus tau. Right? And this tau has been measured from the Lyman-alpha forest. So, the tau f is the effective optical depth in the Lyman-alpha forest that corresponds to the level of tau that is needed to suppress the Lyman-alpha forest to the level that we observe it. Right? And if you plot the effective tau as a function of redshift, here 2, 3, 4, you get these observations. Right? And these were from Fauché-Giguère 2008. I don't know if X commented on the feature that used to be there at redshift pi. It was really redshift pi that was a feature. Right? It was found by 2 different groups, and I remember actually being at a conference, and we really wanted to understand this. Right? It was a real source of concern. In retrospect, it doesn't look that significant, but this was it was really interesting for a while, because I thought maybe this is associated with helium reionization or something like that. But the funny thing was that this feature really was at redshift pi. Now, people have actually done a little bit better in terms of so let me first say, if we think about Lyman-alpha emitting galaxies, we do not really we should not really care only about the mean effective optical depth that has been measured from the Lyman-alpha forest. We specifically care about a very narrow range of frequencies or velocities centered on the Lyman-alpha line, because this is where the Lyman-alpha line comes out from galaxies, right? This is where we need to know what the opacity of the Lyman-alpha forest is. And we know that on small scales it's fluctuating a lot, right? So taking the global average basically and applying it to this very narrow range of frequencies is not necessarily the right thing to do. And in fact, we think it's the wrong thing to do for 3 reasons. Right? We think that galaxies are biased, we know that, and they preferentially reside in overdense regions of the universe. So they preferentially would reside in regions that correspond to these downward fluctuations. The gravitational potential of the dark matter halo that is hosting the Lyman-alpha emitting galaxies is changing the velocity field of the gas. Right? It's not uniformly expanding with the Hubble flow, which is the case for the average IgM. In fact, we think that there may very well be infall of gas happening onto these dark matter halos, at least along certain directions, and possibly, well, depends. The covering factor of these inflows is, of course, depending on halo mass and a whole bunch of other factors, but there is some inflow happening of it. On the other hand, so both these effects sort of turn to increase the opacity of the IgM to Lyman-alpha radiation. On the other hand, we also think that this gas near the galaxy is likely exposed to an enhanced ionizing background, right? So that would reduce the opacity of the IgM. So what do calculations say about this? It would just be nice to see. Well, naively, we may expect the IgM opacity to look something like this on average, right? It should go up as you move closer to the resonance, because this corresponds to gas that is actually physically close to the galaxy. It's denser than average. At the same time, we might expect this absorption to extend to the red side of the line, right? This is really the stuff that is falling onto the galaxy. So what do calculations look like? This is from results by Peter Lauwersen. So this is the average transmission, average over many sidelines, right? And you see exactly what I was talking about, this sort of enhanced opacity at frequencies close to the Lyman-alpha line center, right? And it's at high redshift especially, it's extending to the red because of this infall. Now, Peter,
so I know those of us who are in the SED fitting realm end up sort of using Madao at all. Is this a marked improvement over that?
Well, I mean, Madao et al., that applies to your broadband colors, right? So there you can actually take this frequency averaged transmission that you get from the Lyman-alpha forest. I think the Madao prescription, once you apply to the Lyman-alpha line coming from galaxies, that's very likely not good.
Okay. But broadband's fine?
Yeah, that's fine. Yeah. This is really applying, I mean, this is applying to the Lyman-alpha line from galaxies, and well, as you can see, this can actually be an important effect, right? So that's why I want to show it. Right, and I mentioned before that interstellar radiative transfer provides us with initial conditions that affect even intergalactic radiative transfer. And a simple way to see it is if you just take this transmission curve that I showed earlier and put a Lyman-alpha line through it that is either blue shifted at systemic velocity or red shifted, right? And then ask what fraction of the photons get transmitted. Right? Now if you had a Lyman-alpha line that were centered on the systemic velocity of the galaxy, right, you would transmit less than 50%, right? Only 20%. And the resulting line would be a redshifted line asymmetric, which is kind of annoying because it would look a bit like a line processed through an outflow, right? Now, we do not think this is the reason for the shape of these lines at high redshift, because we see this kind of line shift at low redshifts as well, right? So I think that's actually an important piece of observation to have. On the other hand, if you have outflows, say if outflows redshift your line to begin with, so now you have a redshifted Lyman-alpha emission line, the outflows actually can cause a line to shift into the regime where the IgM is not affecting it much at all. Right? So outflows can actually make Lyman-alpha emission sort of immune to intergalactic scattering, which is nice because then you don't have to worry about it. Right? On the other hand, if you have inflows, for example, if you have Lyman-alpha photons scattering through a collapsing cloud, it somehow comes out on the blue side. Well, it comes out on the blue side in this picture. That flux may actually be killed very efficiently by subsequent scattering on intergalactic scales. So just to drive this point home that interstellar radiative transfer is really affecting subsequent radiative transfer a lot, right? So is there a way to actually, is there a way to test this at high redshift? And I think there is. And it's been shown, and I don't have a slide on this, but it has been shown that you can imagine that, for example, in the case where you're very sensitive to scattering in the IgM, you can imagine that if you have galaxies residing in denser parts of the IgM, to be less visible than galaxies that reside in low density regions of the IgM. Right? So that's for a survey like HEDDEX, for example, which is selecting galaxies on the basis of Lyman-alpha emission. A survey like HEDDEX might have a harder time finding galaxies in overdense regions if intergalactic radiative transfer were very important. Right? So I think one of the things that HEDDEX will be able to measure is whether there are contributions to the clustering of Lyman-alpha selected galaxies due to radiative transfer effects. Right? Radiative transfer can actually modify the clustering of these Lyman-alpha selected galaxies on very large scales even. And that's potentially interesting. And yeah. So these dark energy measurements might actually constrain, I mean, if you think about it, it's pretty bizarre. So you have large scale, a dark energy experiment, and the clustering of Lyman-alpha selected galaxies on very large scales might actually tell us something about the scattering process on interstellar scales. Right? So I think this is, for me, this is quite cool. Okay, intergalactic radiative transfer during reionization. I think I have 7 minutes. So let me just start with this is a movie that I made myself. I'm really proud of it, so please don't laugh. But okay, this is the expansion of the universe. You see the universe expand. As the universe expands, it gets darker and darker. Darker. Okay, thanks. Yeah, it gets darker. As it redshifts further and further away, it gets darker. Right? All the visible radiation gets redshifted into the infrared, so it's pitch black. So these are the dark ages. In the dark ages, a lot happens. Right? We have gravitational potential wells are growing, and these gravitational wells are building up and building up, collecting their baryons, until at some point the first stars form. Right? Once the first stars form, they start emitting their UV radiation and start creating ionized bubbles around them. And then the clustering properties of these very first sources start driving the collective growth of ionized bubbles. Basically, these bubbles are powered by multiple galaxies each. Right? So each of these bubbles that you see here, ionized bubbles, you're really making the universe transparent again to ionizing radiation. Right? So in one of these bubbles, there will be many, many galaxies powering this, its growth, basically. Well, it's funny, like I thought I almost saw a face in there, but I don't think that's possible. Right. And I think understanding this process is very interesting from a theoretical point of view, because we know that this growth of these H2 bubbles is closely related to the nature of the very first sources, so whether they are stars, accreting black holes. This really affects the precise growth and bubble distribution. Right? So we'd like to understand how this happens exactly. And even during the dark ages, accreting black holes can heat the gas, etc., and all of this affects the thermal evolution of the thermal and ionization history of the universe. Right? And this is something we're going to probe in the next 10, 20 years. Right? Now, what is interesting about this inhomogeneous reionization is that it really promotes the visibility of Lyman-alpha emitting galaxies. And that's shown by this cartoon here. If you have a large H2 bubble, and we think these bubbles can be hundreds of megaparsec co-moving large, right? They can be tremendous, especially at the late stages of reionization. That makes a huge difference for observing Lyman-alpha emitting galaxies. If you have a galaxy in an ionized bubble, which is where we think most of the galaxies are, the Lyman-alpha photons can actually redshift away from resonance, as indicated by the color, before they first see their neutral intergalactic medium. And that boosts their visibility, right? Because then, once they're far away from resonance, the cross-section goes down, the opacity of the IGM basically goes to zero. It becomes smaller. Right? Now the same redshift can be mimicked, as we knew, and we know very well, by scattering through galactic outflows on interstellar scales. Right? We know that outflows redshift align. We see this observationally. We see that all redshifts. Now if this happens at high redshift, that basically means you need a smaller bubble to render these galaxies visible. Right? So there's two ways in which we can render these galaxies visible during the epoch of reionization. So Masami posed this question in his lecture. So he says, what allows us to see Lyman-alpha emission from galaxies deep in the reionization era? Well, there's two effects. It's ionized bubbles. We think these are there if we understand reionization, and I think at this stage we do understand it at this level. And outflows, right? We think outflows affect Lyman-alpha transfer as well, and exactly in a way that promotes their visibility. Right? Which makes it actually even weirder to, how much time do I have?
3 minutes.
3 minutes, okay. Right. Let me think about what to do. Right, well, you know what, I'm just going to do this in 3 minutes. You know, so I'm basically arguing that in inhomogeneous reionization, it's not so difficult to see Lyman-alpha emission from considerably neutral universes, right? Now this is why it is so surprising that we see Lyman-alpha emitters disappearing beyond redshift 6, right? This has been a puzzle for a while now. Like what Masami was showing is that both the luminosity function of Lyman-alpha emitting galaxies, which is not evolving much between redshift 3 and redshift 6, it drops beyond redshift 6.5, right? Or even beyond redshift 6. Similarly, the Lyman-alpha fraction drops quite fast beyond redshift 6. It depends a bit on the continuum magnitude of the sources, but they drop. And what is interesting is that you can actually predict the redshift evolution from this population based on this population alone. I won't have time to go into this, but it just suggests that we're seeing this drop purely because the Lyman-alpha photons themselves are experiencing extra opacity, which is not seen by the UV continuum, right? And the only thing that can do that is neutral hydrogen, right? So the question is where that neutral hydrogen is. And so what has been puzzling about this observation is that in inhomogeneous reionization, we expect the Lyman-alpha emitters to disappear very subtly, right? If the universe is 20-30% neutral, we should not see this. It should not be this strong. At least that's what we think, right? And so these observations, explaining these alone, you can only get if the universe were significantly neutral, right? So 40-50% at redshift 7, which is a bit crazy. But the weird thing is, of course, that the Planck measurements, I just want to show you like how little we actually know about reionization at the moment, right? So and that Lyman-alpha is actually adding something, right? These are the best constraints on the reionization history that we have right now. These are from the quasars, right? The Gunn-Peterson trough that we see in quasars, inferring a neutral fraction from this is very difficult, right? And because of the inhomogeneous nature of the reionization process. If you take that into account, you cannot really say much about the ionization state of the IGM at redshift 6.4 even. It's less than 25%, which is much weaker the constraint than what you usually see when you look at the old papers. And the reason is that the old papers were putting constraints on the neutral fraction of hydrogen inside ionized bubbles, right? We think quasars sort of populate the largest bubbles that exist, and these quasars likely populate very large bubbles, right? So if you take into account the inhomogeneous nature of the reionization process, you cannot say that the universe was much more neutral than, or much more ionized than 75%. Right? So this is I think one of the best model-free upper limits we have at redshift 6. Now you put the Planck constraint here, right? This is the midpoint of reionization by Planck. This is the uncertainties, right? So we don't really know so much. And these are the results that people have proposed for Lyman-alpha emitting galaxies. Right? So it's actually, it is kind of consistent. Now, I was in a meeting last week, and Planck is actually doing this. Right? So Planck is coming down further. Right? So, I mean, I think it might actually look like we have late reionization. Right? So this is quite surprising, actually. Oh, yeah, and do I have time for 1 minute?
Yes.
1 minute? Okay, I have a joke. Great, excellent. So we have a lower limit on the neutral fraction from the Lyman-alpha fraction, from the disappearance of Lyman-alpha emitting galaxies. Masami, I think it was Masami actually, that published an upper limit on the neutral fraction based on Lyman-alpha emitter clustering at redshift 6.5. And that puts the universe at less than 60%, 50% neutral. So we have an opportunity here, right? The universe was less than 50% neutral at redshift 6.6, but it was more than 40% neutral at redshift 7. So that can mean only one thing. It means that the universe was 45% neutral at redshift 6.7. So I showed this at a conference. I was like, I'm so happy that we've now finally entered the era of precision reionization, right? And some people were actually quite worried about that. In any case, I'll stop here. So if you have any questions about any of this.
Well, I'm going to talk about polarized transfer, all right?
Sorry.
Talk about polarized transfer, all right?
You're going to reveal us that top 3 starts.
Unmute. I was really close to going to the bathroom with it on.